Hi, I'm Zor. Welcome to Unizor education. Continue talking about inverse matrices. Let me just remind you the definition which we actually came up with in the last lecture was that if you have a matrix X, let's say, then the inverse matrix is the one which we symbolically use x to the power of -1. If it's multiplied by our x on the right, it will give an identity matrix, or on the left will be exactly the same result. We were also talking about matrix X to be a square matrix, dimension n by n, which necessitates the inverse matrix also to be of the same n by n dimension. And so obviously is the dimension of the identity matrix, where all the diagonal elements are ones and all other elements are zeros. Now we have defined this, that's fine, okay. We also investigated certain properties. For instance, certain matrices do not have inverse, like the matrix, for instance, with one row equals to 0. We already discussed that in the previous lecture, and we have also proven that if the inverse matrix exists, then it must be unique. There are no two different inverse matrices for a given matrix. Now, all these discussions left alone one very important aspect. Do inverse matrices exist at all? You see, it's a very important quality of any definition. If you define something, it's important that you define something which really does exist. And then you can investigate the properties, like if it exists, then. But this existence is a very important thing. So today I'm going to spend a relatively short period of time to talk about existence of the matrices which are inverse of some other matrices. And in this particular case, just for simplicity, I'm restricting myself to a square matrix of 2 by 2 dimension, the simplest matrix which can be actually considered. So what I'm going to do is I'm approaching constructively this question of existence. So I will take a matrix, a square matrix of 2 by 2 dimension, and I will attempt just to find an inverse to this matrix. If I'm succeeding, it actually means that inverse matrix does exist, at least in the 2 by 2 case. Well, if I fail, it means there are no inverse matrices, and it doesn't really make any sense to define it anyway, right? But I will succeed. So let's do it, and our purpose is just consider any matrix which is a square 2 by 2 matrix, and I will just take its coefficients as A, B, C, and D, and I will try to find another matrix with unknown coefficients, unknown elements, W, X, Y, and Z, such that their product is equal to an identity matrix of 2 by 2 size. All right? So I consider this to be like an equation, basically, where this matrix is unknown, this is a known coefficient, and this is the known result. Well, if these are not matrices but numbers, let's say you have number A times number X equals number B. I know how to derive the solution to this. If A not equal to 0, this is a condition under which this actually does exist. The solution does exist. Then X is equal to B divided by A, right? So I know that. So now I'm looking for something similar in the world of matrices. But let's just consider we have 4 different elements, so it's 4 unknowns. Now, matrix multiplication is actually certain number of rules which we can derive and really multiply these rows by these columns, etc., to get this. And we will get certain number of equations, actually 4 equations, because for each element of the result we have certain linear dependency between the components. So let's just do it. We will have a system of linear equations with certain number of unknowns, and we will just solve it, right? Simply. Okay, how to multiply 2 matrices? To get an element 1, 1, first row and first column, we have to multiply as scalar product first row, vector row, by first vector column. So it's AB times WY, which is AW plus BY is equal to 1. Next, how to get second row, first column, 2, 1, element 2, 1, second row, first column. Well, it's second row and first column scalarly multiplied. And this is 0. Now this 0, first row, second column, first row, second column, AX plus BZ equals 0. And the last one, second row, second column, second row times second column, CX plus D0 equals 1. So this is a system of 4 linear equations with 4 unknowns, and actually it's simpler than generalized system because it actually can be considered as 2 independent systems. You see, there are only W and Y here and only X and Z here, so I can separately solve this system of 2 equations with 2 unknowns, and separately from this system of 2 equations with 2 unknowns, X and Z in this case. So let's try to solve this one. We will multiply, well, I want to get rid of Y, so how do I do it? I multiply this by D, and this by B, this by D, this by B, and subtract. So what will be? It will be AD minus BC W equals D minus 0 D. That would be from this, right? AD W BDY subtract BCW and DBY. Y will be cancelled out, and I have AD minus BC. Yeah, that seems to be correct. From which I can derive W equals D divided by AD minus BC. Okay? Now, okay, let me write it here. W equals, actually, yeah, alright. W equals D divided by AD minus BC. Okay. Now, if I will multiply, now to get Y, I have to multiply this by C and this by A and subtract, right? So this by C and this by A and subtract. It will be ACW and this will be ACW and subtract. Okay, so I will have BCY minus ADY equals to C, right? Now, mind you that this is, in parentheses, almost the same as this one except the sign. So I would like everywhere to have the same, so I will put Y equals minus C divided by the same AD minus BC. So I change the sign here and here. Okay, So this system is solved. Now this one. Very similarly. To get rid of z, I multiply this by d, this by b, and subtract. So what I will get? Z will be cancelled. AD minus BC, AD minus BCX equals, now this is by d, this is by b, minus b. From which I conclude that x is equal to minus b divided by the same thing. And finally, to find z, I multiply this by c, this by a, and subtract, and I will get bc minus ad z. Now this is 0, this is a minus a, right? Or again, I reverse the signs, and I will get a over ad minus bc. Okay, my system of 4 equations with 4 variables is solved, and what's very important is that it is solved with one and only one condition. Because it's the same denominator for every one of them. So, if this condition is preserved, then my answer is YW, so it's D minus C minus B A, right? Divided by AG minus BC, which is not equal to 0, right? Since every member, every element of the matrix has this coefficient, I will just use the multiplication of the matrix by a constant. That's exactly the same thing. So to multiply the matrix by a constant means actually multiplying each element by this constant. So D minus C, okay. So as you see, inversing this particular matrix seems to be very easy. You change the A and D, and you reverse the signs of B and C. Well, let's check if we do get the result of this if we multiply this by this particular matrix. All right? You know, checking is always the good thing if you solve the equations, right? So let's just check. Let's forget about this for a while. We will multiply the result by this factor afterwards. But right now we will multiply A, B, C, D by D minus B minus C A. D minus B minus C A. Okay, let's multiply. First row by first column, AD minus BC. Okay. Now let's go down. Second row, first column, CD minus DC, 0. Now first row, second column, AB with a minus, so it's minus AB, and BA, 0. And finally, second row, second column, second row, second column. Stop. Something is wrong. Oh, second row, here. Second row, second column. Minus BC plus AD. So AD minus BC. So that's my matrix as a result. And with this factor, this will be 1 and this will be 1, which is exactly the identity matrix. So I have derived with a correct solution of this equation. This is my matrix A, B, C, D minus 1 to the power of minus 1, which means inverse matrix, okay? So the inverse matrix to A, B, C, D is D minus B minus C A with a factor 1 over AD minus BC under this condition. So this condition is necessary and sufficient to get this solution. Just as a side issue, this expression is called a determinant of the 2 by 2 matrix. And we have a special topic, determinants, matrix determinants, which is already on the website. So any matrix has this kind of an expression called determinant, which is just one real number, which concentrates a lot of power telling something about the matrix. So in a way, it's equivalent of comparing the numbers, the real numbers, with 0. So whatever the properties of the real numbers relative to their being equal to 0 are true or not true. For instance, we cannot divide by a real number equal to 0, right? In the matrix world, a similar concept is the determinant of the matrix. If it's equal to 0, it's not a good matrix in some way, which means, for instance, it does not have an inverse. And there are some other things which I am actually talking about when I will be talking about determinants in other lectures. But anyway, for a 2 by 2 matrix, this is a determinant. And this is the way how the matrix is supposed to be inverted. That's basically it, because something like uniqueness and some other properties of inversing of inverse matrices we have discussed already before. Now, if you remember, we were talking about something like linear dependency between rows or columns, which prevent us to have an inverse matrix. Well, guess what? If, let's say, 2 rows are linearly dependent, then determinant is equal to 0. Well, just as an example, look at this. If you have 2 linearly dependent rows, let's say 2, 4, 6, 12, what's the determinant of this matrix? Well, it's 2 times 12, right? AD, this is A, this is D. So the determinant equals 2 times 12 minus 6 times 4, which is equal to 0. If some more complicated dependency, linear dependency exists, the result will be exactly the same. Or among rows. Or if one row is completely equal to 0. For instance, if this is 0 and this is 0, well, this times this is 0 minus this times this is 0. So all these separate cases, which I was considering in the previous lecture about inverse matrices, which prevent us to have an inverse matrix, they're all combined together in one inequality. The determinant is not supposed to be equal to 0 if we want to find an inverse matrix. Well, that's it for this lecture. I do encourage you to go to Unizor.com, go through the notes for this lecture, and if you are a registered student, you will be able to have certain problems solved, exams. Your supervisor or a parent can enroll or unenroll you in certain courses, etc. So it's a little bit more more interesting work with this particular website. Well, other than that, this is it. Thank you very much and good luck.